Nick Karpowicz. Nick is actually from the Albany, New York area. He says upstate New York, but since this is a short drive from Ottawa, I thought I would be more specific. He's from the Albany, New York area. He got all of his degrees from RPI, Rensselaer Polytechnic Institute. After that, he moved to Germany and took a position at the Max Planck Institute for Quantum Optics in Garching, and he's going to tell us about some of his research there.
So thanks very much to the organizers for inviting me here and taking care of me while I've been here. So today I was going to talk about some of the research that we've been doing over at the Max Planck Institute. And mainly what I'm going to focus on is Attosecond science, so using some of the technology that you saw in the previous talk, but more focused rather than on photoelectron spectroscopy, using the information contained within characterized electric fields in order to go back and look at what was going on inside of solids. So all of this is based on being able to measure optical electric field waveforms, which is kind of a new thing that came out in the past decades based on the availability of ultra-short attosecond pulses. So you saw before in the last talk, so I won't belabor the point. In this high harmonic generation process, so we take an electron, it's ripped out of the atom at, say, a peak of the laser field, accelerated out in the vacuum, and returns at a known point in time, emits its excess energy as a XeV photon, which can then be shaped into an attosecond pulse. In order to use this pulse to measure a laser electric field, we need a second step. So for this, we've made extensive use of the attosecond streak camera. There are other techniques based on using high harmonic generation to measure fields as well, but this is the one that we've been using most. And the basic idea here is you do a photoemission experiment, so you send in this XeV pulse into, for example, a neon gas atom, together in time and space with the same infrared laser field, which was used previously to generate the attosecond XeV pulse. And the basically remaining part of the electric field of the laser will accelerate the electron around and cause a shift of the electron energy in time. And by mapping the momentum versus time delay between the infrared field and the attosecond field, you can measure the vector potential of the laser. There's actually a lot of other physics based on the photoemission process itself that's been interesting to look at in the attosecond range. But for the purposes of this talk, I'm interested only in this fact that the laser is encoding its waveform onto the momentum of the electron. So why is it interesting to measure the electric field of a laser pulse other than just knowing what you're working with in the lab? The basic idea that I'd like to get across is that when you have a laser field or any kind of electric field interacting with electrons or other polarizable things inside of a solid, the laser field is causing some changes in the material, and the electrons are responding to the laser field, but through their motion they're also leaving their own imprint on the field at the same time. And kind of the history of the motion of electrons inside of the solid is written back into the laser field that was causing them to move around in the first place. So by recording these waveforms of the electric field versus time, there's a signature of the motion of all of the charge that the laser had induced on its way to the measurement. And by doing a careful measurement of these electric field waveforms during different kinds of interactions, we can kind of tease out what these electrons were telling us, kind of writing it into the field as they were moving around. So in order to do this, we use this attosecond streak camera to record these electric field waveforms. For example, at 2 different intensities of the laser field interacting with the material that we want to study. And by recording one waveform at very low intensities where the interaction is mostly linear, and one at a higher intensity where the interaction becomes nonlinear, we can start to see subtle changes in the shape of the electric field. And by studying these changes, we can actually figure out what happened to the electrons while the field was there. The basic idea is we take these 2 waveforms and look at the small difference of them and interpret this through the nonlinear propagation of light inside of a solid. So if you just take the 1D wave equation, reduce it to a first order equation, you can learn how to do this in Bob Boyd's book. You can write out the nonlinear wave equation like this, so describing how the electric field frequency components are evolving inside of the material you want to study. And it basically has these 2 terms, one describing the linear light propagation and one describing the nonlinear polarization. You can write this in an integral form, and these first 2 terms here on the left-hand side, this E at position Z, this will be the electric field at the end of the material that you're studying. And this one is the electric field at the beginning and then linearly propagated through the material. And these are essentially these 2 waveforms that we measure in the experiment. So the remainder is this final term containing the nonlinear polarization. So we just need to extract this to get the dynamics of the electrons inside of the solid. The tricky bit is it's stuck inside of this integral here. So in order to get it out, we just do a Taylor series expansion. And if you just solve it to 0th order, you can write an easily analytical solution of this. Turns out for attosecond accuracy, the 0th order isn't good enough in general, but you can make use of an extra trick where you evaluate this at the midpoint of the crystal, and then you have a cancellation of all of the odd order error terms, and you recover the next leading error term. So that seems to work pretty well, and we can apply this to materials such as in this example here, what happens in silicon dioxide when you apply a strong laser field. So we can measure these 2 electric field waveforms, do the same processing, and then at the midpoint of the crystal, we can evaluate these 2 quantities. So what was the electric field and what was the nonlinear polarization? And by looking at these in detail, there's some interesting things that pop out. So the change in refractive index, so the nonlinear refractive index, we have a view of really directly in terms of cycle by cycle resolved dynamics in the time domain. And you can see this is changing nicely linearly as you increase the intensity of the laser. So this seems to be acting just like pure Kerr effect. But interestingly, at the higher intensities, this nonlinear polarization is not responding instantaneously to the electric field of the laser. At the lower intensities, where things seem to be really just pure Kerr effect, it's almost instantaneous in time, at least within the accuracy of what we can measure. But as you crank up the intensity above 10 to the 14 watts per centimeter squared, a small delay starts to show up of a few tens of attoseconds. And this seems to scale with the intensity of the 4th. And we can kind of understand why that happens by putting these 2 measured values in a more suggestive form. So this is essentially Ohm's law that describes the energy transfer between the electric field and the material system based on the electric field and nonlinear polarization in time domain. So really the derivative of the nonlinear polarization, which is a current. And this gives the energy transfer into the material. And you can see at low intensities, There's a bit of energy moving into the sample, that's positive direction on this curve, and then it just goes back down to basically 0. So the sample was polarized by the laser field. There was some energy stored by the polarization, but that was just re-radiated as coherent light with the electric field as it was leaving. But you can see as you start to turn up the intensity of the laser, there's a little bit of energy that's getting left behind, and at least on this time scale, it just stays there inside of the solid. And this is what happens when the electric field is strong enough to induce multi-photon transitions into the material, and makes charge carrier pairs, storing energy 9 eV at a time as they cross the band gap of the solid. This whole intensity of the fourth scaling you can understand pretty easily in terms of multi-photon absorption, where the lowest order fully resonant term is the 6-photon transition, and if you do the math, it works out to the delay scaling with intensity to the fourth. And this leads to a nice interpretation you can do of what this delay in the nonlinear polarization means. If the electric field is following the nonlinear polarization, so the polarization is driving the field, there's an energy transfer from the material into the field. Whereas if the polarization is being driven by the electric field, the energy transfer is in the other way into the material. So we thought this was pretty cool. You can really look at cycle by cycle what's going on inside of the solid. So both the generation of charge carrier pairs and this transient polarization of the material. We wanted to make a little more use of this latter effect, or first effect, the generation of these carrier pairs, and start to think of what kind of electronic effects can happen at this time scale. So this is what I wanted to call attosecond optoelectronics. So in general, optoelectronics is the interface between light and electron motion. And in the attosecond regime, this is things that are typically coherent and ballistic, and it leads to a pretty tight correspondence between optical wave packets and electron wave packets. And optical waves are now something we have pretty good control over. And how good or how well does this control that we have over the optical waveform translate into control over electron wave packets in solids, and can we put this to use for something? So the answer is yes, but first we need some extra tools to make the study a little easier. So as I was talking about before, the main reason I was using attosecond streaking was to measure electric field waveforms. But in different frequency ranges, for example, the terahertz range, electric field measurements are fairly standard things that you can do with electro-optic sampling, for example. So electro-optic sampling is a field measurement technique that you can read about in quite a long history of papers in the terahertz range, for example, where you take the waveform that you want to measure and a laser pulse short enough to fit within half cycle of the laser approximately, and send them into a second order nonlinear crystal for electro-optic sampling. So you make use of the Pockels effect, where this electric field induces a birefringence inside of this crystal and changes the polarization state of the sampling pulse. And then you use a balanced detection scheme in order to measure the polarization changes as a function of time delay between these two waveforms. And that gives you your electric field as a function of time. And that works excellently in the terahertz range. It gives you huge dynamic range, great sensitivity for electric fields, and the only question for us was, can we make it fast enough to work? So last year we published a bit about this, so we got it up working into the near infrared regime. So the full details of this experimental diagram aren't that important. The thing just to look at is we use a 4 femtosecond pulse generated through a titanium sapphire laser. and do two things with it. We generate our infrared light through difference frequency generation in a BBO crystal, recompress this white light, and use it again for electro-optic sampling of the same difference frequency light after a few amplification stages in an OPA, which we actually don't need. We can look at the unamplified signal as well, but for us in the lab, the amplified signal was a bit more interesting. And you can measure this electric field waveform. And if you compare its Fourier transform with what you measure on a grating spectrometer, you can see it works pretty well. So this got us up to a detection limit of about 240 terahertz. Recently, we've pushed it a bit further, so synthesizing this kind of single cycle infrared pulse with spectral content up to about 400 terahertz here, so corresponding to about 700 nanometer wavelength. So we can detect visible light with electro-optic sampling now. So we wanted to start using this for looking at electron motion in solids, so we needed a test system in order to look at this kind of motion. And what we do is we use the same pair of pulses that we can use for electro-optic sampling. So some test waveform here, and in this case our short white light pulse, and use this white light pulse in exactly the same way that you saw on the polarization spectroscopy to drive multiphoton transitions inside of the solid. And once you inject some charge carrier pairs, they'll feel this weaker test field and be driven around and result in some net current that we can then measure with these electrodes. The process of driving around electrons in a solid looks surprisingly similar to what happens in attosecond streaking when you eject an electron into the vacuum. So in the strong field approximation, the motion of an electron is just its original velocity that it gets from the photon that kicked it out, and then it just gets shifted around in time by the vector potential of the laser field. You wouldn't think that it would be so simple inside of a solid, because you have electrons in delocalized states that are overlapping with billions and billions of other electrons, but Bloch's momentum theorem, acceleration theorem, lets you use the crystal momentum in a very classical way, which corresponds pretty well with what you see in attosecond streaking, with the difference being that this quantity that you're working with doesn't correspond exactly to the free space motion of the electron. That's just related through the band dispersion. So if I draw a cartoon of how this looks, so you have this red field here, which basically is just serving to shift around the electron inside of the Brillouin zone. This lucky electron happens to be shifted to the gamma point at the time that the strong field arrives and causes a transition, and then the rest of the field just puts it back at its original K point. And this leads to a asymmetric population of the conduction and valence bands. So now, in comparison to attosecond streaking, where we'd only be concerned about this electron up here, the electron was originally in a delocalized state where it had kind of a job to do before, which was to cancel the motion of all of the other electrons in the filled band, which it isn't doing at the moment. So you have some current which is due to the presence of this hole here and the electron up there. But the effect is still the same, that you have a momentum imbalance, which results into a real space velocity of the electron, which is proportional to the vector potential. And we can test this just by comparing, doing this measurement with attosecond streaking and doing the same measurement in this current sampling setup using the same pulse. So the blue and the red are what we measure with attosecond streaking and the field-induced current. Using the same laser, slightly different setup. So the blue pulse had to make an attosecond pulse first. But other than that, it's the same laser pulse. And you can see most of the details of the waveform are exactly the same. And I mean, what's interesting here is before I was describing this process is essentially delta function, that the transition happens at one point in time. But of course, the transition rate is a function of time, which gets convolved with the vector potential that you measure. And we can actually make use of that fact by changing this response function as a function of, for example, the carrier envelope phase of the laser. So by changing the details of the waveform, we can modify when and how the transition takes place. So just by changing the electric field waveform and repeating this measurement for different carrier envelope phases, we can take the Fourier transform of this to get a spectrum of the wave that we measure here. And in principle, when you change the carrier envelope waveform of a pulse, the spectrum doesn't change. But in this case, you see the spectrum that we've measured does. You can see there's this dark area here. If I normalize it just to make it a little more obvious, you see this blue blob here where the spectral response at the frequency of the laser disappears for certain carrier envelope phases. And we can reproduce this pretty well in a simple multi-photon model of the transition dynamics. And what this whole corresponds to is when, rather than taking place in one burst of excitation, as I was assuming before, that it takes place in two bursts of excitation. So one at each high intensity half cycle of the electric field waveform. And so because you have two bursts, one taking at one half cycle and one at the other half cycle, if you're driving this around with an electric field at that same frequency, basically one part of the wave packet gets accelerated one way, one gets accelerated the other way, leading to zero net current. If I take lineouts through that last plot, you can see what these transition rates look like in the time domain. And the one with the big dip corresponds to this red curve here, basically an effective double attosecond pulse, whereas the blue curve, where you have the flat spectral response, corresponds to a single attosecond effective pulse with a sub-femtosecond duration. We can look at a bit more of the details of this. So it'd be interesting to know with kind of exact precision relative to the intensity of this injection pulse when the transition happens. So when does this charged carrier pair start acting like free electrons that we drive around? And we can do this now with electro-optic sampling because we can use the same pulse pair really simultaneously, or at least sequentially, without changing any of the system, just by directing it to electro-optic sampling or to this kind of sample here, and measure the same waveform, in this case generated through difference frequency generation. And this allows us to do two things. Again, to reconfirm that they measure essentially the same electric field with slightly different spectral responses, but you can see the waveforms that are measured are extremely similar. And we can actually look at small details of any temporal offset between these two waveforms that we measure. And something interesting comes out of this, which is that as you increase the intensity of the laser, the timing of this transition seems to change. If you're working at lower intensities, there's a bit of a delay on the order of hundreds of attoseconds, which tends to approach zero as you turn up the intensity of the laser. This is essentially a detail of the multi-photon absorption, which is happening at lower intensities, where it's basically only into a selected subset of states which are building up coherently. And as you turn up the intensity of the laser, you're accessing more multi-photon channels, more states in the system, and the whole thing dephases faster, leading to a effectively faster response time. So this seems nice. It seems we've confirmed that it's measuring the electric field of the laser. And then the question is, what are the limits? So this is what Sean and Dimitri have been doing lately. Sean recently left us in Germany and actually joined Paul Corcom's group here in Ottawa. So lucky you guys. And what they did is started to generate different waveforms through various nonlinear processes in either difference frequency generation crystals or one's phase matched for some frequency generation, and using this to cover the spectral range from about 5.3 microns up to 275 nanometers. And this is a full petahertz of spectral bandwidth, which is covered by this system without having to change anything about phase matching or anything like that. It seems to just have that full spectral response, which you can see is nicely linear, and we're able to detect the electric field of waveforms on the energy scale of a few nanojoules. And of course, since we have this working in the lab now, we're starting to use it for that attosecond polarization spectroscopy I mentioned before, where we can compare two different waveforms passing through test materials at different intensities, and doing this a lot more easily because we don't need these huge vacuum beamline systems that were necessary with the XEV. This is just taking place on a tabletop and letting us do some of the experiments that we could only do with the attosecond beamline before. So we can do things like looking at energy transfer again, and also looking at other nonlinear processes as they unfold, such as second harmonic generation inside of a BBO crystal, where you can see all of the effects of the group velocity walk-off really in real time inside of the crystal. So I'd like to conclude just by saying, by measuring electric fields, we can tease out a lot of interesting details of light-matter interaction. And there are now multiple ways of doing this, and some of them don't even require vacuum or high-energy photons. And this allows us to do or look at a lot of interesting things going on inside of solids. So we can look at really the time evolution of transitions inside of solids, and use these to kind of carve out effective attosecond pulses that we can use for measurements inside of solids. And we can combine field detection techniques to look at detailed timing of transition phenomena. So I'd like to thank you for your attention. These are all of the people that I'm working with at MPQ, and these people kindly provide us with funding. So thank you very much.
So Nick, thank you very much. We're open for questions, discussion. Let me go first, and then you second. So, why do you think it took so long for electro-optic sampling to be applied outside of the terahertz?
So if you take just this 4 femtosecond pulse out of the laser and try to do electro-optic sampling in kind of the standard way and do your best to phase match it, you'll still lose a lot of the high frequency response here. But there's a trick that we learned from actually Rupert Huber's group, where they were using a short pass filter in their system to pick out just one part of the sum frequency generation that comes out in the electro-optic sampling process. And this allowed them to improve the signal to noise ratio of their system. And I started playing with it, and I realized that you can actually reshape the spectral response of electro-optic sampling by doing spectral filtering here. And so this allowed us basically just to select the right filter to have a flat spectral response in the infrared range, where otherwise it would just be falling off exponentially as you go to higher and higher frequencies.
Okay, thank you. And there's a question here. You showed in the figure when you send a pulse, as you increase the pulse intensity, there's a pedestal. If you go back to the figure, the first one.
So earlier on, yeah, here.
Do you think if you keep increasing, you will have like a second step or a third step, or?
So if we go to higher and higher intensities, what's going to happen here?
Looks like first you get one step, and just thinking about it, I thought maybe if you keep increasing, you will get a second step, or?
Well, I mean, these two steps that you see here, this is a combination of two effects that are happening at one time. So you're polarizing the system, so you're kind of coupling valence and conduction band states. But before the pulse ends, the electron doesn't know if it made a transition yet or not. It's just in some superposition, and the time evolution of the rest of the field is going to determine if it made the transition or not. So at this point, you have a combination of excitation and polarization. So electrons that are going to stay in the conduction band and electrons that are going to come back down. I think if we were able to turn up the electric field higher and higher, there would be more kind of processes that would make electrons in the conduction band, which should show up and have some signature here. But if we turn up the electric field higher in this experiment, it just cracks the sample. So we can't go too much higher.
Time for one more question. Is it here?
How long the electric field that we're measuring can be?
Right.
Okay.
Is there upper bound? How long can you
Not really. So.
measure, say, much longer?
Right. I mean, people in the terahertz range, people, I mean, especially people who want to do gas spectroscopy can scan for nanoseconds and measure the electric field there. I mean, the thing is for pulses like this, I mean, for example, if I was going to send a picosecond pulse in, I could spectrally filter this and just carve out a picosecond pulse with this. It's just at that point, electro-optic sampling might get a bit tedious because you have to look at every single field oscillation in this picosecond pulse, and there are easier ways to measure a field like that. But for these short pulses, it works out okay.
So, Nick, thank you very much. Let's thank Nick again.